Welcome to CFD Engineering, I'm Rob, the lead engineer. In this episode I'd like to show you the thermal simulation of the new design of a servo motor electronic controller and how you can save time on the setup process by reusing files of the initial design in SC Tetra. You may well remember from the previous episode that we had a small vertical PCB card with two silicon chips which were feeling quite hot under the casing. These chips nearly reached the blazing 90 degrees C when the ideal would be 60 or below. I had to do something to reduce their temperature, so here is what I will try as the first step in the design process. I relocated the vents both on the top and on the bottom, and I will show you a comparison with the old one in a second. When I removed the casing, you can see that I also added two small aluminum heatsinks to the chips on the tiny vertical board. My aim is to add conductive mass with fins to help carry the heat away. Let's compare the initial and the new casing design. I didn't change the vent open area, but I pushed the cuts closer to the front of the unit so that these would be right above the vertical board. On the bottom side, I again pushed the vents towards the front, so these would be underneath a series of small chips on the bottom card, which were also too warm. These are all the changes. They were easy to implement in the CAD environment, so let's see how they perform. After loading the CFD model in, you can see that I have the same ridiculous amount of closed volumes and materials as in the initial design. Not in a million years I want to go through this list and name the parts one by one again in the design change, but luckily I do not have to. The CFD code can restore part volume names for me from another model. When I pick the initial model, the software ranks the parts in terms of how well the old fits the new. At the top of the list it tells me that two new parts did not match any old ones, and it also shows a long list of parts with almost same as the original volume node, which is sweet because all these volumes are recognized. The two it could not handle are the newly added heatsinks, which will not have assigned material numbers, so they are easy to find and easy to add aluminum properties to them manually. I also add these two to the group that has all aluminum parts in it. As far as the mesh element sizes are concerned, I let the CFD tool build an automatic mesh of 5 million elements using the same settings as with the initial design. When it is done, I start to manually make the mesh of those parts uniform that will have wattage on. To do this, I use the volume groups the CFD code recognizes for each material. For example, this is how the mesh of everything made of polystyrene looks. But I want to show you something that will further speed up the process and provide some backup if I mess up the element sizes. I can log the manual mesh refinement process and play it back later on. I give the log a name, do the manual mesh refinement and stop the log recording when the polystyrene is done. I move on to the next volume group and record a log for each separately. This way I have a recording of the manual mesh refinement of each material group, or any named volume or surface region actually, which I can play back anytime I want. As the log contains mesh elements selected by the material group name, I can replay this log to refine mesh of any future design changes, supposing that I will have the same material group or region name as the log file is based on. Here is all the mesh refinement logs applied, one by one, to the 5 million base mesh again to show you how fast it will be for the next design change now that I have these log files. I have the mesh element sizes ready. Let's move on to boundary conditions. I do not want to do the wattage setup procedure again, no way. Instead, I let the settings file of the initial design handle it. I look up the S file of the old simulation, which has every setting I previously used. All I need to do is to change the name of the mesh file, the name of the restart file, and the name of the results file in the header section and save it with a new name. When I drop the new settings file into the simulation, it tells me which boundary conditions are missing their regions. All I need to do is to register these. When I save the settings file, the system tells me if any other regions are missing. These ones are related to the panel feature, so I do not want to delete them, but I go back to region registration instead. I set up the missing contact region on the big aluminum block and then reset the panel edge contact condition with the new contact region on the block and the new casing. When I save the S file, the system shows no more missing regions, so I'm all good to go to calculate mesh and run the solver. Alright, let's see what the results show. The initial design is on the left, the design change is on the right. With the steel casing on, not too much difference is visible, but if I remove it, you can see that my efforts were not entirely in vain. If I change the minimum value of the scale, you can see that the temperature of chips on the vertical board did decrease. That is good, but they are still above 80 degrees C, which is not so good. The ideal would be 60. Numbers show a 6.9 degrees C decrease, and another adjustment of the scale minimum shows that there is an effect of the repositioned bottom vents, as chips on the bottom card are a tiny bit cooler. The change is between 0.6 and 0.7 degrees C depending on which chip I'm looking at. Airflow around the vertical card is different. Warm air can get out of the casing more easily, but at the end of the day, all that matters is component temperature, so to sum it up, this problem has not been solved yet. This design change would be just the first step in a real-life product development process. Also, without thermal simulation, this design change would have been built and tested. Both would have taken several days and the problem would still be there. What design change would you recommend to solve this overheating issue? Let me know in the comment section. I hope you enjoyed this episode. Please subscribe if you haven't done so, because more interesting CFD simulation stuff is coming. Thank you for watching. See you next time.